Uh-oh, this isn't good. Chemical is slowly leaking onto a floor. Let's hope it's like water or diluted hydrochloric acid or something gentle. Alright, anyway, the chemical spreads out from the point where it lands in a shape that can be modeled by a circle. Alright, so just imagine this is the first drop. As it spreads out concentrically, so from a center in the shape of a circle. Cool. Now, as it does that, its radius will increase, right? The circle's getting bigger and bigger as time goes on. In fact, at time t, the radius is given by 0.1 t plus 2. Cool. So at 0 seconds, the radius is 2 centimeters. At 1 second, it's 0.1 plus 2, so 2.1, and so forth. Use calculus to find the rate of change of area of the circle with respect to time when its radius is 10 centimeters. Right, that's a mouthful. Keyword, rate of change. Rate of change just means the gradient. So at some point we will need a function and we will need its gradient function. Right? The rate of change is the gradient if it's with respect to time. But we're actually looking for that gradient when the radius is 10 centimeters. So at a particular radius. Cool. So we know, let's jot down what we know. We know radius is 0.1 t plus 2. Great. So looking at the second part of the question, when the radius is 10 centimeters, we could substitute in 10 to work out the time. So let's do that first. So when radius is 10, subtracting 2 from both sides, dividing both sides by 0.1, we know at 80 seconds, so after a minute and a bit, the radius of this circle will be 10 centimeters. Cool. Alright, so we know the time value, but we want the gradient function so that we can substitute the time into the gradient function to work out the rate of change at a radius of 10 centimeters. So they've kindly given us area of a circle as pi r squared. So the area is pi times the radius squared, but in this case our radius is in terms of t. So 0.1 t plus 2 squared. Yep, so just expanding those brackets out. Always good idea when you're expanding, just write it out in full so you don't miss the middle terms. So we have 0.1 times 0.1, 0.01 t squared plus 0.2 t plus another 0.2 t plus 4. Right, and those middle two terms will combine to plus 0.4 t. Alrighty. Plus 4. Okay, so all as we've done so far is we've used the area of a circle, pi times the radius squared, where the radius is 0.1 t plus 2, and we expanded it. So from here, this tells us how the area changes with respect to time, or in terms of t. We can work out the derivative of the area with respect to time. right, or a prime. So working out the derivative of this equation. So the pi can stay out the front, and just looking at the brackets, the power, so 2 times 0.01, 0.02, subtract 1 off the power, 0.4t becomes 0.4, plus 4, the derivative is 0. Great, so we found the derivative of the area with respect to time. In other words, how the area changes, right? The gradient function. Now we can put it together. So earlier we worked out the radius is 10 centimeters when time is 80 seconds. So substituting in time is 80 seconds into our rate of change of area will give us the rate of change of area of the circle when it is a radius of 10 centimeters. So dA with respect to dt, if you want to be fancy, you could write this line. So evaluated at time equals 80 is equal to pi 0.02, substituting in 80 for t, plus 0.4, pi 0.02 times 80, what's that, 2/100ths, so 1/100th is 0.8, 2/100ths is 1.6, plus 0.4, adding those gives 2, so we're left with 2 pi. So the rate of change of area with respect to time at 80 seconds, which is when the radius is 10 centimeters, is 2 pi. What a mouthful. Now what are the units for this? So area is units centimeters squared, but it's the rate of change of area with respect to time. So centimeters squared per seconds. Okay, that's a lot. So let's recap that one. It is an excellence question. So unfortunately for us, there is no achieved component to this question, but the merit component is finding the derivative of area. So that was this part here. So that's where we use pi r squared. We expanded it out. We then calculated the derivative with respect to t. And after that, we then knew we had to substitute in 80 seconds because that's when the radius was 10 centimeters. And if we did that correctly and got the final answer correct, that is excellence. Units are optional. However, I would say an understanding of the units actually makes this problem a little bit easier. Alright, see you next time.